Welcome, students. And once again, we're going to continue talking about the basics of chemistry as we introduce this week here. And we mentioned several days ago that when we're studying chemistry, the main things that we're studying are matter and energy. And yesterday we defined matter and what that is and how we classify matter into different categories. And so that is definitely important. But the second half of chemistry, and we'll probably spend more time dealing with the energy aspect towards the second semester, is energy. And that's what we're going to be looking at. And this comes into play a lot of times when we're talking about chemical bonds and chemical reactions. What we're going to measure, what we're going to look at is energy being released or absorbed, how much energy is released, why is energy released, all of those kind of things we'll deal with. And so understand that energy is going to be a big topic when it comes to chemistry, and we talk about chemical bonds or chemical reactions. Energy will always play a huge role. So let's start by defining energy, just like we define matter. Energy also is one of the simplest definitions. And its definition that you find in just about any textbook is typically defined as the ability to do work that's really actually not so much the definition as a description, because there's really not any good definition of energy per se. So it's more of a description of what energy does, and again, that's fairly broad, the ability to do work. Okay, well, what is work? You kind of go to the realm of physical science or physics and kind of define, well, what is work? And again, that's a huge, broad category in terms of what that is. So we're going to look at some various forms of energy, and then I'll even have a picture here, graphic, that we can kind of show. You guys probably can think of some different forms of energy without looking in your book that go on in the world around you. Some of them are obvious, probably as you look up at the ceiling. One is mechanical energy, so making things move. You think of, if you go up to Tehachapi area and you see all the windmills, that would be mechanical energy where the wind is pushing on those windmills. Ultimately, it generates electricity, but it begins as mechanical energy. There's movement, there's motion in something there. Thermal energy is another form of heat. Or another form of energy, and it usually comes in the form of heat. This is probably the most common form of energy that we will deal with in chemistry, is the giving off or receiving or absorbing thermal energy. So more often than not, when we're talking about energy in regards to chemistry, it will be thermal energy here. Sound is another form of energy. Obviously, as you project sound, you're projecting energy, and it creates sound waves, okay, that vibrate through the air that somebody else's ear receives. Sometimes it's called acoustic energy. Electromagnetic, the sun gives off a lot of electromagnetic energy. Your microwave would give off electromagnetic energy. Chemical energy is another aspect. Probably a good example of this might be a battery, in which it gives off chemical energy, which we then convert to electrical energy. Nuclear energy, which takes principles that we've learned about the nucleus of the atom, and the nucleus of the atom, or certain types of atoms, emit particles out, and those particles contain tremendous amounts of energy, and in some cases we can harness that, and we use that as nuclear energy. So those are all different forms of energy, and we could probably mention others. Here's kind of a little graphic of some different types of energy. You have nuclear energy, which powers the sun, which then gives off electromagnetic energy, which we could, in some cases we can absorb that. We call it solar. If you have solar panels on your house, you're absorbing that electromagnetic energy emitted by the sun. There's thermal energy, which is heat. Mechanical energy you see there with the windmill blowing around. Like we mentioned, chemical energy from a battery. So there's all different kinds of examples there in terms of ways in which energy is produced. What we're going to focus in on throughout this chapter is kind of, well, what are the basic laws that govern energy? How does energy transfer from one thing to another? and then ultimately what we call the states of matter and how do they relate to energy, because matter and energy are related, and so we don't want to treat them as two completely separate topics. All right, laws governing energy. The main laws are the laws of thermodynamics, and you may have covered these in some form or another. What thermodynamics is, it's the, you see thermal there, it's the idea of heat energy. It's the study and movement and conversion of energy. So how does energy move from one thing to another, and how is it converted from one object to another? And there's some laws that govern this. The first law of thermodynamics is known as the law of conservation of energy. And it basically says energy cannot be created or destroyed. It can be changed form, if you want to add that on there. I would suggest that. Energy cannot be created or destroyed, but it can change form. Or if you want to say it can be transferred. The second law of thermodynamics says that during any energy, and this is sometimes called the law of entropy, during any energy transformation, some energy goes to an unusable form. And both of these laws can be restated in different ways. The second law of thermodynamics will kind of restate in a different way when we deal more with energy and matter in another chapter in second semester. And that's probably the more common way that you've heard it. But right now we're going to kind of take a look at it this way. Basically, the best way to illustrate this would be if you're riding a bike, there's a certain amount of energy that comes from your legs, your body, that you are pushing on the pedals. And then as those pedals turn, that energy gets transferred to the first set of gears there towards the front of your bike, which then gets transferred to the chain, which then gets transferred to the back gears, which pushes that tire, and that tire pushes against the ground. So there's a number of different transfers of energy as you're riding a bike. Not all that energy that started in your legs, though, actually goes into an unusable form or to a usable form. Some of it is not used or is wasted. If you think about it, probably one of the biggest things hindering as you ride a bike is quite simply friction. As the chain rubs against the gears or the tire rubs against the ground, there's some energy that goes as heat energy or friction that we call it. And you need heat energy or friction, but it goes to an unusable form. It's not helping you when that chain is rubbing on those gears or your foot is rubbing on those pedals. That's not helping push the bike forward. It's not going to a usable form. So some energy, it's still there, it's just wasted. So you can't create or destroy energy. And there is actually a third law of thermodynamics. We'll mention it a little bit later, briefly. But in terms of energy, the last law that we're going to mention here is the law of mass or matter conservation. And this is very similar to the first law of thermodynamics. And it says during ordinary processes, mass is neither created or destroyed. Or you could put matter in there. Matter is neither created or destroyed. So it's basically the same idea as the first law of thermodynamics, except now they separate the two. And that'll come into play later when we're dealing with keeping track in a chemical reaction. What you start with, you have to end with. Whatever element, however many atoms I start with or how many molecules I start with, I'm going to have to end with. I can't just have some that are vanishing into oblivion or some that are being created out of nowhere. So that is important to keep in mind. Now, both of those laws actually cause problems for the theory of evolution. How did we get here in the first place? Where did the matter come from? And there's several different theories that have been proposed, none of which are scientifically viable. They're really, if you want to put it this way, a hodgepodge of unsupported philosophy to attempt to come up with a solution to that major issue. All right, how do we measure energy? Well, first of all, what kind of energy are we talking about? In chemistry, we're always talking about kinetic energy, which is the energy of motion. We never talk about potential energy in chemistry. That is more the realm of physics. Whenever we're talking about energy, it is always kinetic energy, energy that is moving, whether it be the atom itself that's moving, whether it be the protons or electrons or neutrons. Okay, there's always motion that we're talking about, the molecules themselves. And we're going to divide this up into two types of energy. One is heat, okay, or what we call thermal energy, and that is the total kinetic energy of all the atoms in an object. So if you were to take, a cup and add up all the energy of all the atoms, that would be what we call heat. The other is one that you're probably more familiar with, and that is temperature, and it is the average kinetic energy of an object. And so when you go out and you take the temperature of the air outside or the temperature of the engine in a car or whatever, it's the average kinetic energy of an object. That's what you're measuring. So there is a difference there. And we use different scales to measure energy, and usually we're measuring temperature. The average is typically what we're measuring. There's the Celsius scale. That's the one we will use most commonly in our labs and things like that. We will not use the Fahrenheit scale. This is the scale that's used around the world and in science. So you'll find it, if you travel to another country and they have the temperature, and it's 27 degrees out, your mind is probably thinking that's really cold, but really it's actually a nice temperature because it's on the Celsius scale. Fahrenheit is what we use here in the United States. It's not conducive to being used in laboratory situations. It's not a good scale. The Celsius scale is 0 to 100. 0 in terms of freezing. 0 is freezing. 100 is the boiling point of water. I would know that if I were you. Kelvin is used mostly for measuring extreme cold. And it's the definition of absolute zero. You can't get any lower than that. So you may want to know this. 0 degrees Kelvin is what we call absolute zero. What is absolute zero? It's basically the point at which all the molecules or atoms stop moving, or there is no more energy. And that's what we call absolute zero. All the energy in a substance has been removed. And we'll talk about a little bit later how you convert between the scales. That's not something I'm going to do in this presentation, but we will cover that a little bit later. Okay, there are two terms briefly to know, and that is, and when we're talking about reactions or chemistry, there's a term called exothermic, which simply means that that object or that reaction is releasing energy into its surroundings. And most reactions are what we call exothermic. That's the way God designed the universe, is that typically things want to release energy. Endothermic, those kind of substances, they absorb energy from their surroundings. So those are our two different terms, and I just want you to be aware of those. It'll be a couple chapters before we really deal heavily with those terms, but I do want you to be aware of them. All right, as we get into the states of matter here, we first want to start with this, what's called the kinetic theory of matter, and that simply says that atoms that make up all substances are in constant motion. Some of it might be a little bit of motion, it might be a lot of motion, but they're always moving. Okay, so that's something to keep in mind. And we want to quickly take a look. What are the four states of matter? The first one is the one that has the least amount of motion or energy in it, and that is a solid. And the official definition here is a material having a definite volume and a definite shape. Key thing I want you guys to remember is it has very little energy. Then you have a liquid, which has a little bit more energy. Those atoms in there are moving more rapidly, and as a result, it still has a definite volume, but it doesn't have a definite shape. Okay? Then you get to a gas, which has a lot of energy, and so those atoms and molecules have moved away from each other. And then last you have is a plasma, where there's so much energy that literally the atoms are having difficulty breaking apart. What you have are ionized particles, basically. And we'll explain a little bit more. So how do they change from one state to another? You have a bunch of terms in your definition sheet, so I'm going to go real fast here. And a lot of these are common sense, but you will need to know these on the test. Okay, melting, what is that? That's changing from solid to a liquid. That's kind of a no-duh. Evaporation, changing state from liquid to a gas. Now this occurs at the surface. So if you have a pot of water and it's boiling, the evaporation is what occurs at the surface. Boiling is what occurs at the bottom. Okay, it's the bubbles that you see that are changing from a liquid to a gas. Condensation is a state from a gas to a liquid. So as things cool down, those molecules are slowing down, they have less energy. Freezing is going from a liquid to a solid. And then sublimation, the last one here, is the odd one, and that is where you kind of skip that middle phase. You go straight from gas to a solid or a solid to a gas, without going through the liquid state. All right, we are done.